Welcome students, and today this is the second part of Green's function. What we are going to do is basically construct Green's function. Okay, construct one sec. Okay. Green's function, yeah, for a ball. So as I told you, yes, as I told you that Green's function can, no, I mean, you can, of course, we saw that for a given domain, let's say omega is a sufficiently smooth domain, you can actually, I mean, construct a Green's, you can actually get a, representation of, I mean, formula for u of x, right? But the problem is, the problem is to construct the Green's function for such a domain, yeah? And for most domains, it's not possible, yes? But for some particular domains it is, and one such domain is a ball. So definition, let's we start with the finding Green's function. So essentially we have to find the corrected function, if you remember, yes? How to find the corrected function, and for that we are going to define some new concepts. So definition, okay? So let if x is in Rn minus 0, yes? So x is non-zero vector, then the dual of x is given by okay. So basically we say x has a dual if x and the dual will look like this: x tilde is x by mod x square. So if you most of you understood what it means, yeah? It's called the dual of x is given by x tilde, which is by definition x by x tilde. So essentially what we are doing is we are basically taking the inversion of x with respect to the ball, okay? So this mapping, the map x going to x tilde, okay, is called the inversion through the unit ball, okay? You see, I will make all of this clear why we suddenly started with something like this and what exactly does it mean. So let's understand more in details what it means. See, essentially, let's say this is your R2, right? Let's do this R2, and that's your ball. Sorry, okay. Yeah, please forgive my art. It is not very good. Yes. So let's say this is your unit disk. Yeah. And now what happens is, let's say I'm starting out with the x here. Yeah. On the point, on the boundary. So x is on the del b, let's say 0, 1. Okay. Then mod x square is what? It is 1, right? And therefore x tilde will be x by mod x square, yes, which is x. So basically, if you reflect x with respect to this unit ball, the boundary, with respect to the boundary of the unit ball, yeah, that remains the same place, right? It does not change direction or anything. I mean, nothing changes. So x and x tilde are same in this case, right? So the inversion of x. So basically, you are inverting x. You understand? So think of this as a mirror, kind of a mirror, and you are putting a point here. You will put another. You will get another point on the other side of the mirror. Something like this, yeah. So, but if you are taking a point on the mirror itself, so on the boundary, x is equals to x tilde. Now, for example, let's say x you are taking it to be something like I don't know, maybe let's take 1 1, yeah, 1 1. So definitely that's not a point on the boundary, and it is outside the ball. Let's say 1 1, yeah. So as you can see, x tilde will be half. Okay, that's inside the ball, right? Half. Okay. So you see a point here, if you take, so this is your x, and then x tilde will be inside here. Okay. So something like this. What it says is, if x is on the boundary, then x is equals to x tilde. If x is here, okay, then x tilde is inside the ball, in the disk, in the disk, yes. So x is there. So basically the reflection you can think of, or vice versa. If x is here, then x tilde is going to be outside the ball, yeah, something like this. So basically we are inverting the point with respect to the boundary. I think this is clear now, yes. So if it is not clear, so what I suggest you to do is please take 2-3 points and look at what exactly does it mean. Clear? Okay. Now the thing is, you remember what we are trying to do? We are trying to compute. So basically, we are trying to let's write down our aim. Yeah, we are trying to construct Green's function for a ball. Clear? We are trying to construct Green's function for a ball. Yes, this is our motive. I mean, this is our aim. Yeah, that's our aim. And to do that, what we are going to do? We are going to first of all construct a character function. Yeah. So construct a character function. So for that, we are going to fix. So fix. You remember, I want to fix a x in the domain. So in this case, the domain is b01. Yeah. Once I fix this thing, the character function, and define the character function. Character function for this fixed x, Cx of y, as Laplacian of Px, okay, is 0 in b01, and phi x of y equals to, this is the fundamental solution phi of y minus x. Okay, this phi and this phi is different. Yeah, this is the fundamental solution. This capital phi. This is the small phi on the boundary of the domain. Okay, this is what we are taking. So basically, for a fixed x on the ball, you take any x on the ball and you define a character function which is satisfies Laplacian of Px is 0 on the ball, and Px of y is capital the fundamental solution at y minus x. Okay? Now you see, this is well defined because y here is always on the boundary, right? In this case, y is always on the boundary. X is in the center of the x is on the ball. Yeah, y is on the boundary. So essentially, y minus x is defined. So phi of y minus x is defined here. Yeah, so y cannot be equal to x, and hence it is defined. So and the Green's function, and once you get this character function, the Green's function, what is it? What is the Green's function? Will be g of xy is the fundamental solution at y minus x minus phi x of y, right? Yes. So that's your Green's function. Now, how do I find this character function? That's the question. Yes. Okay. So what is the idea? The idea is to invert the singularity. Okay, let me tell you what I mean by this. See, essentially, I want a function which is, say, I want to find phi of x. See, once I find phi of x, I already know what my fundamental solution is. Just put it there and it's done, right? So all I need to do is to find a character function. Now I know that the character function, what does it do? It is actually the fundamental solution. Yeah, the value of the fundamental solution at y minus x. Please understand this thing. What is y? Y is, in this case, y is on the boundary. X is a point on the ball. Clear? Inside the ball, inside the open disk, open set B. Now, here this is defined, no issues. If you define, let's say, if you define phi of x to be the fundamental solution, of course it is 0. Laplacian of phi is 0. But for all x not equals to y. Okay? Is this clear? So, you see, here there is not a problem because y is always on the boundary and x is in the interior of the ball. Okay, so y is never is equals to x. But here, if you are putting phi of x to be, so let's say, if I am taking phi of x to be our fundamental solution of y minus x, okay, then for some y, okay, we have y equals to x, right? Of course we have. X is any fixed point in B01. There is some y where in the ball there is some y where this has to be same, and when this is same, this actually blows up, right? Yeah. So this is not a good option in the ball. So basically what we want to do, we want to find a function which is the fundamental solution, the value of the fundamental solution at y minus x on the boundary, but phi of x is 0 in the interior of the ball. You do understand what I'm saying? Okay. So let's try to construct such a thing. So you see, that is why we want to invert the singularity, because there is a singularity. Definitely there is a singularity if I want to do something like this. Yeah, at x equals to y. So let's just invert the singularity. So what we are going to do is for x in B01, clear? We have x tilde definitely not in B01. So outside B01, right? Yeah, it is in the complement. Yeah. So so for now, let's just assume n is greater than equal to 3. Yeah, this is just an assumption. I mean, you can do it for n equals to 2 also, no problem. Yeah. So assume. See, I mean, you have to do it in two different sets, but for n equals to 3, I'm doing n equals to 2 is exactly the same thing. Nothing changes. Okay. So assume this. Now you see y going to tell me something. Phi of, think about it, y minus x tilde is harmonic, okay, for y not equals to x tilde. Yes, this is true. Why this is true? Because you see, if I'm taking y which is not equals to x tilde, so phi is harmonic everywhere in Rn, right, except at y equals to x tilde. So that is why it is harmonic as a function of y. Now, if that happens, thus one can say that y going to mod x power 2 minus n, the fundamental solution of y minus x, is harmonic for y not equals to x tilde. Same thing. See here, essentially this is a function of y. So if I'm multiplying it by mod x to the power 2 minus n, does not matter. I mean, the same kind of idea. It's basically a constant as far as this is concerned. Okay. See, for a fixed x I'm doing, right? I have fixed the x. So basically this is a constant. I'm just multiplying it by a constant. So harmonic function remains harmonic. It's not a problem. Yes. And therefore, hence, you see, if I'm writing phi x of y, okay, define phi x of y to be the fundamental solution of mod x times y minus, sorry, this is x tilde. Okay. So this is harmonic in B01. Is this clear? Why it is harmonic? See, y going to this is harmonic for y not equals to x tilde. Yes. Where is our y? In our case, we are choosing y from the ball. Yeah. X is definitely never in the ball. It's outside the ball. So basically, this is always harmonic in this B01. Yeah. If I define phi x of y to be the fundamental solution of mod x times y minus x tilde, then that is harmonic in B01. Yeah. Now, you may say that what's the point of putting this mod x to the power 2 minus 1? This is phi of y minus x is actually harmonic in B01. You are right there. But the problem is, you see, if you do that, you understand what I'm saying. What is the point of this multiplying it by mod x to the power 2 minus n? If I don't do that, then what happens is, this is true that capital Phi of y minus x tilde will be harmonic in B01. But I also have to have that phi x of y has to be phi of y minus x on the boundary. Okay. So this I want to calculate. Yeah. This I need to have. Yes. So for that, what I am going to do is this. See, if y is in del B01, okay, so that is why I am multiplying with this particular mod x to the power 2 minus 1. So let's say if y is on the boundary of the ball and x not equals to 0, I am choosing x not equals to 0, okay, then mod x square mod y minus x tilde square, yeah, let's calculate this thing. I will show you what is happening here. Mod y square minus 2 x dot y by mod x square plus, so I will just break it up, plus 1 by mod x square. Okay, so it essentially is, see, mod y is on the boundary, so mod y square is 1, so essentially this is mod x square minus 2 x dot y plus 1, correct? So which is mod x minus y square. Clear? So essentially what is happening here is, thus, let me write it, thus mod x mod y minus x tilde power minus n minus 2, this is equals to mod x minus y to the power minus n minus 2. Yeah. So, and therefore what is happening is phi x of y, this is equals to the fundamental solution of y minus x, okay, for y on the boundary of 0, 1. Is this clear? See, I want my phi of x, I want my phi of, where is it? Yeah, I want my phi x of y to be the fundamental solution at y minus x. It should be equal to the value of the fundamental solution at y minus x. Yeah, if I'm choosing only this thing, not with mod x to the power 2 minus, not with this. If I'm choosing only phi of y minus x, that is never going to be phi of y minus x tilde, right, on the boundary. Yeah, so for x in B01, yeah, it cannot happen. So for that I am modifying this thing, I am multiplying it by mod x to the power 2 minus 1. Once I do this, then for any y on the boundary, you can show that mod x to the mod x times mod y minus x tilde whole power this is equals to mod x minus y whole to the power n minus 2. For n greater than 2, this is the fundamental solution, right? So phi x of y, this is your phi x, right? So phi x of y is basically capital phi, the fundamental solution at y minus x. Yeah. So this is what? This is our phi x y is defined by the fundamental solution of mod x y minus x tilde, which is essentially this. So that is why phi x of y, I wrote it like this. Clear? Okay. So consequently, this is happening. So let me write down that, therefore the Green's function, the Green's function. How do you write Green's function? The g of xy will be defined as the fundamental solution of y minus x minus the fundamental solution of mod x y minus x tilde. Okay, this is for xy in B01 such that x not equals to y. Is this clear? You see, the fundamental solution minus phi y, that is our Green's function, and phi x of y is essentially our, this is the fundamental solution. With respect to fundamental solution, it is written like this. Yeah. So the corrected function is in terms of fundamental solution. So g of xy is this. Okay. So now assume, I'm just doing a particular thing. You see, once you find this Green's function, you know how to write u of x. Yeah, so that is always there. So let us solve a small problem using this thing. Yeah, so let Laplacian of u is equals to 0 in the ball with center at 0 and radius 1. Okay, so basically this is ball with center at 0 and radius 1. So please remember, if I am not saying generally in this course, whenever I am saying B01, you just think of it as a ball with center 0 at radius 1 until I say otherwise. Okay, and u is g, yes, on the boundary of the ball. Okay, so let's say this is given. So I am not taking f. Let's just start with Laplacian equals to 0, harmonic. So therefore, you use the representation formula. If you use the representation formula, you can see that u of x will look like minus integral over del b01 g of y del g del gamma of x comma y d s of y. Clear? Okay. So u of x will look like this. This is where is it coming from? You remember in the last lecture we talked about the representation formula. Representation formula. Clear? In the representation formula, there is another part, but that part is 0 because of Laplacian u equals to 0. Okay, that part is not there. Essentially, it is boils down to the boundary. Okay. Now, for this, let's just solve this problem and see if we can do this. Yeah. So basically, you see, if I want to solve this problem, if I just calculate this thing on the boundary, then I'm done, right? I just put it in the G and I'm done. Okay. So let's just do that. G of here. I'll just show you how to do this thing. So G of yi, you remember this is basically, what is it? It is G y. So the derivative is with respect to y. Okay, whatever, I don't know what express, let's just call it like this. Yeah, this is just a notation, whatever notation you want to write it. It's not a problem. So essentially this is del G del gamma is this one, right? So what is del y? With respect to c, basically I am taking g of x is a function of two variables x and y. I'm just taking the derivative with respect to y. Is this clear? Okay, and that y is y1, y2, yn. So basically I just have to take the partial derivatives and after that put it together. Okay, so let's just put that out. So basically if I just write it down, then del g del gamma is summation. It will look like this: del g del yi gamma i. Okay, I equals to 1 to n. It will look like this. Yeah. Okay, so I just have to calculate del G del yi first. So that is what G yi. This is. I hope all of you guys know these notations. Yes, G yi is del. This is just a notation. This is just a notation. Okay, this one is just a notation. That's what I'm saying. So this is equals to the fundamental solution with respect to y minus x minus capital Phi of mod y, y minus x tilde. Okay, and this is with respect to yi. Maybe I can write it here, yi. Okay. Okay. Now, once I do this thing, let's calculate this one. Capital Phi yi mod y minus x tilde. Okay. Do I really need to calculate? You guys can do it yourself, right? Let's just write it down. 1 by n alpha n. See, you know what phi is, right? You just calculate the derivative with respect to yi. That's all. Yeah. This is xi minus yi by mod x minus y whole power n. Yeah. You guys already know how to do this. It's just you write phi and take the derivative with respect to yi. That's all. Yeah. And also, sorry, what am I doing? It should be phi of y minus x. Okay, the first expression. Now, and you also can do the same thing here. Mod y minus x tilde. What exactly is this thing? Again, if you calculate, again, I'm not doing this thing. Yeah, I'm just writing it down what exactly happening. So you have to check this part. Yeah, minus 1 by alpha n yi mod x square minus xi by mod x minus y whole power n. Okay. So see, please let me be very clear about it. You already know what phi is. Yes. Just put what phi is on this variable and after that take the derivative with respect to yi. Yeah. I am absolutely certain that all of you guys can check this part. So please do that. Yes. So once you do that, what do I need to do? Once I do that, then yeah. So u of x will look like this, right? So I just have to put it there. You see, del G del gamma is essentially this thing, right? And gamma 1 I of y I already know. I will just put it there and I will get what my del G del gamma is. So let's say therefore del G del gamma at the point xy. What does it look like? It will look like summation, as I wrote it here, I equals to 1 to n. Okay, yi g yi at the point xy. Now I don't think you are wondering why yi is there. What is gamma? You see, this is del G del yi at gamma I. What is gamma I? Gamma is the unit outward normal and that's a ball. So basically this is y by mod y, right? So, and mod y is 1 here. So, essentially that is not there. So, gamma is y. So, gamma I is yi, right? So, that is why it's yi. So, this is the unit outward normal at the point y in the ball. Okay, that's the unit outward normal. Now, unit ball. Yeah. So, yi is equals to gamma y, the unit outward normal component on the boundary. Clear? So that is this. Now, if this happens, you see, you just put it there, yeah, minus 1 by n alpha n 1 by x minus y whole power n, okay, summation I equals to 1 to n, okay, yi minus xi minus yi mod x square plus xi. Okay, I'm not doing anything. I'm just calculating this. I'm just putting it together. Del yi of this thing, yeah, is del yi of this thing. I'm just writing it, and then minus of this particular thing, yeah, because phi yi of y minus x is this. So minus of this particular thing. If you just put it together, summation with the summation, it will look like this, no? Okay. So once I have this thing, calculate this thing. Once you calculate it, what is going to come out is this alpha n 1 minus mod x square by mod x minus y whole power n. Okay. Okay. So please remember, where is y? Where is in this? Yeah, you can't choose y from anywhere, and you can. So because you see here, y is on the boundary of the ball. We want y from the boundary of the ball. Okay, I don't care what y does outside. So basically, all of this calculation is for y on the boundary of the ball. Okay. Once I do this thing, what is our therefore from representation formula? From representation formula, one has u of x will look like 1 minus mod x square by n alpha n, okay, integral del b01, okay, g of y by x minus y whole power n ds y. Clear? Okay. Now this is on a ball with center 0 and radius 1. Yeah, you can of course do it for a ball with center 0 and radius r. So on B0R you can do that. Yes, that's not a problem. So in B0R, okay, you can write it like this. See, this is on B01. This is on B01 in B01, right? So if I ask you to do it on the ball with radius r, of course you can do it. You just change u to u tilde, which is, so basically you just replace u to u tilde, which is u of rx. So you see, in a ball with center 0 and radius 1, this is the formula. So in a ball with center 0 and radius r, you just have to scale u accordingly, right? So that is x is getting scaled to r of x. That's all. Yeah. And similarly, g will get b. I mean, you have to do it like this: g of rx. Yes. Once you do this thing, what do you get? You get u of x will look like r square minus mod x square, r by x, yeah, by n alpha n r integral over del b0 r. I mean, there is nothing special. I mean, it's just I am writing like this, x minus y whole power n dsy. Okay. This, and see why I suddenly did it for B0R, because I wanted to write this k of xy. Okay, so this k of xy given by r square minus mod x square by n alpha n r, okay, and 1 by mod x minus y whole power n. Yeah, so x is in B01, B0R, and y is on the boundary. Okay, this particular thing is called the Poisson kernel. Okay, for the ball B0R. Clear? So what I meant is this. See, this is the representation formula for B01. If you want to do it for B0R, you just scale it. You just scale U and G, and you have what is U of X. In this is U tilde of X. Yeah. For the ball, the formula will look like this. So it's not U tilde, basically U of X. For the ball, if the solution is U of X, then that is given by U of X to be this. Yeah. And see here, the main idea of writing is this. Writing this is the following. I just want to write this r square minus mod x square by n alpha and r times 1 by 1 minus x whole power n. This is a kernel. Yeah, this is called a kernel. This is a special kind of function. It's a singular function actually. Yeah, this is the kernel, and this kernel is called the Poisson kernel. Yeah, Poisson kernel for the ball B0R. This is very important. We'll look at why this is important later. Yeah, in an assignment I will show you. When you can see that what is so important about this Poisson kernel. Okay, there are a lot of things which you can do with this thing. So that is why. So I'm just ending up with this small theorem which I'm not going to prove, because this proof is exactly the proof of what we did earlier. Yeah, for that convolution thing. So the existence result in ball. So let G is a continuous function del B 0R and U be given by let's say, I don't know, let me call it 3 maybe. 3 is given by 3. Okay, if that is the case, then number A, U is in C infinity. You can show that this is infinitely differentiable on B0R. Is this clear? Okay. See, initially what we did, if you remember, that we did the convolution of the fundamental solution with F and showed that this is C2. Yeah, given F is C2. So here what we are saying is, if you are given G which is continuous on del B0R and U is given by 3, yeah, then U is infinitely differentiable. Laplacian of U is equals to 0, because we started with Laplacian of U equals to 0. See, we started by solving this problem. Laplacian U equals to 0 equals to G. Okay. So what the theorem says is, you can show that U is infinitely differentiable. Laplacian of U is 0 in B0R, and C, you can show that limit. How is the boundary condition satisfied? This is what, yeah, limit x tends to x naught. Okay, x naught, and x is in B0R. Okay, U of x is equals to G of x naught. See, U is such that on the boundary it is G. What does that mean? It means that U of x, see, inside I know what U does, right? So I'm saying that at as U tends to x naught, G, so basically what will happen is Ux will tends towards G of x naught. That is how it is satisfied. Okay, for each point x naught on the boundary of the ball with radius r. Okay, so the proof is exactly the same what we did, so we are not going to do that thing, but I think it is more or less clear. So let us summarize what we did here. Once you find a Green's function, so basically you have to find a corrector function. Yeah, to find the corrector function in this case of ball, what we did is, we basically look for the inversion, right? We look for the inversion. Once we say here, where is it? Yeah, we look for the inversion of a point x tilde. Why do we look for inversion? Because there is a singularity at x equals to y. I just don't want that singularity, so we look for an inversion and made the function harmonic. Why did we multiply mod x to the power 2 minus n? Because we had to match our corrector function on the boundary. That is why we multiplied by mod x to the power 2 minus n. Yeah, let me write it. we multiplied by mod x to the power 2 minus n here because phi x has to match capital Phi of y minus x on the boundary, right? Yeah, that is why we did this. Now, once we did this, yes, we know that these are harmonic, and we showed that this is the reason why it matches on the boundary. Okay, and then you write down the Green's function. You already know what phi of x is. There is nothing else. You use the representation formula, write it down, and calculate what g is. Put it together, and yes, you get this representation formula. This is u of x. So the value, this is the value of u at any point x. Yeah. So the representation formula. Now, do you think there is another formula for u? No, because you see the point is u is unique, right? So whatever the value of u at that point, this is the unique value. Okay, because of uniqueness theorem for this problem. Okay, so and on B0 what you can do is you can just scale the domain and the functions appropriately, and you get a solution like this. Please remember, this is important. This is called a Poisson kernel. This kernel is called Poisson. See, G, nothing special is there. G is given to you and we just incorporated G. This is important, yeah? And this is called a Poisson kernel, okay? And what did you get? The U which you get from here, that U is C infinity. Laplacian of U is satisfies this 0, and boundary condition is satisfied in this way. So basically, you take any point on the boundary, yeah, that is getting approached by u. So basically like this, limit u x tends to x naught, u of x goes to g of x naught. Yeah. So with this we are going to end this